Hello, I'm Katherine Kretke from Southwest Research Institute in Boulder, Colorado. I do communications and public outreach for the NASA Lucy mission. In just a few weeks, in the pre-dawn hours on October 16th, the Lucy spacecraft will launch from Cape Canaveral, Florida, to become the first spacecraft to explore the Jupiter Trojan asteroids. These asteroids are small bodies that orbit the Sun at the same distance as Jupiter, leading and following Jupiter in its orbit. Scientists hypothesize that the Trojan asteroids have been trapped in these special orbits for billions of years, so they are effectively time capsules of the early days of our solar system. Thus, they hold vital clues about the origins of the giant planets and the solar system as a whole. No spacecraft has ever seen these asteroids up close before, so all we know about them comes from Earth-based and Earth-orbiting telescopes. From Earth, each Trojan asteroid appears to be a single, unresolved point of light. But if you observe an asteroid closely, its brightness generally varies with time. One reason an asteroid's brightness might change with time is because of its shape. Let's say an asteroid was longer along one axis than along the other two. As the asteroid rotated, different parts of the asteroid would face the Earth at different times. The asteroid would appear brighter or dimmer depending on what part was visible from the Earth at that time. The way that the asteroid's observed brightness varies with time is called its light curve. This light curve is one of the few clues available to scientists as they work to determine the shapes of these distant bodies. Of course, real observations aren't that clean. Real observations have uncertainties. Also, it is often impossible to observe an asteroid continually over a single rotation. So scientists take advantage of the fact that asteroid light curves generally repeat themselves and use a technique called folding the data. Here, they plot the data as a function of the phase angle, basically a number that varies from 0 to 1 as the asteroid goes through a full rotation, instead of time. Your challenge is to develop a tool that allows users to explore how the shape of an asteroid affects the appearance of its light curve. A few things to keep in mind. As you search for resources, note that many celestial objects have light curves. You may come across discussions of light curves of binary stars, transiting exoplanets, and other stellar objects like supernova. This challenge focuses on the visible light curves of asteroids that are illuminated by reflected sunlight, not self-luminous objects. Also, you'll find it useful to work with shape models in this challenge. A shape model is a way to describe the 3D structure of an object. You can find some shape models of known asteroids on the websites listed in the challenge, but you also might want to start with simpler objects, like an ellipsoid. And potentially, you may eventually want to look at more complicated objects and explore how these complex shapes affect light curves. There are various proprietary and open source software that will allow you to illuminate these shape models under different lighting conditions. Remember that the sun illuminates these asteroids in space from a long ways away, so make sure to use parallel light to illuminate your objects, not a point source. To take this challenge to the next level, you could make a tool that allows users to modify the shape of an object or add brightness variation to the object's surface to make it match an existing light curve. Maybe you can make a tool to help our team get a better idea of what the Lucy spacecraft will see when it first encounters the Trojan asteroids in 2027.